is also an object, which is actually really offers some interesting possibilities, but I won't really get into that. I mean, if you really want to access that, you can actually do something like 3 dot, and actually it's underscore, and that's a little one of these funny little hidden Python attributes called class. So you can access the underscore class, and that actually gives you back its type object. Okay. So everything in Python is an object. You can create, whenever you create a variable, you are by definition creating a new instance of some type. You can manipulate objects and you can destroy them. You can explicitly use the del keyword, or you can simply just declare them inside of a function and exit out of the function and everything declared that goes right. Okay. So again, what objects are? They're an abstraction. They're an interface for accessing the stuff in there. They define behaviors, they define interactions, but they hide the actual implementation that goes on. And this is really what's called object-oriented programming. It's just one way of doing things, but I tend to think that this is really, really appropriate for biology, and it's basically the heart of what's called agent-based programming, where we have individual agents or actors in the system, and all of them have some internal representation, and then they react, and then they interact with the things around them, basically using an interface. And if you think about that, it's exactly how a cell operates, where a cell has some internal, really complicated machinery. It has all the cytoplasm and nucleus and RNA, all those little fun internal things. They're really, really complicated, but at the end of the day, the cell defines a membrane. In fact, the actual definition of a cell is you have a membrane that separates internal complex machinery from the outside world. And that membrane exposes an interface. It exposes little receptors and ion channels where certain messages can get through from the outside world into that cell, and that cell can communicate with its outside world through these little receptors and channels on its membrane. So that is, in a way, that is, the cell is an object. And the cell membrane with the collection of receptors channels defines the interface that that cell has to its outside world. Okay. So for example, this list 1, 2, 3. Its type is a list. We can manipulate them. We can extend them, grab its index. We don't know, and we don't care how Python actually stores its internal structure. I mean, in fact, for a list, it's actually pretty complicated. I'm not going to show anybody because I'm sure most people would probably get scared. So we don't care about its internal behavior or its internal implementation. Okay. So we need to make a distinction between creating a class and using an instance of a class. So creating a class involves defining the class name. It involves defining attributes, okay? And then using it simply involves creating instances of that type. So to create your own types, we use the class keyword in Python. So the syntax there is we use class, and then you come up with a name for the type. In this case, we just happen to be using the word coordinate, and then parentheses, okay? Now, object. So what object there is that's what's called the base class or the parent class. And that is the class that the new class you're building extends. You don't have to put anything there. You can leave that blank. And if you leave it blank, it will simply extend the base built-in object. So object is a type, and so we can do object. So you can do type object. Yeah, it's object load. And that's a type. So a class definition, it's similar to a function definition. But with a function definition really defines just a mapping of a set of results to a set of inputs. But a class definition actually defines a structure, and a class definition, you can have many different methods or accessors in there. Okay. So coordinate is a subclass of object. Everything in Python is eventually a subclass of object. Okay. So attributes. So objects generally have what are called attributes. You have data attributes, which are you can basically think of them as bits of data that are attached to that object instance. So we really haven't done a lot of those. We could do an example like this. So you can do class, my class. I'm going to leave this blank. And you can put different attributes in there. Okay. Then methods are actually functions that are attached to that class, and we actually used a lot of those. We called dictionary.keys, dictionary.values. All of those are methods that are attached to that object instance. Okay. Methods, they could either return stuff or they could perform some calculation with another object. So when we create an instance of an object, we always call its initializer function. And then we define its initializer function with this funny little underscore underscore init underscore underscore. Okay, so let me give you an example of that. So I'll coordinate. Okay. I'm going to go ahead and leave the object blank because it's at default. Okay. And then I make a function definition in here, just like we did for other functions we defined, def. But then instead of giving a regular name, we use funny little init. Okay. And then self. Okay. The first argument to any method you create in a Python class should be self. So basically what this is when this method actually gets called, the self is a reference to this object instance. Okay. And then what we do here is we can do self.x is x, self.y equals y. Okay. So what I've just done is I've defined properties on this object. Okay. So I define an init method and give it two args, x and a y and a self. and they'll set the X and Y properties on this object. So now I can do C equals, and then the syntax here is you simply call the type name. Okay, great. So C is now an instance of a coordinate. C has these properties on it. C dot Y Z. Wow, attributor. Well, you know what? That's because I didn't define Z. All of the properties defined generally go in the init method. If you do not have a statement in your init method that assigns that property, and if you don't have something above it, there are some special things you can put above it to create properties, but we won't really go into those. They won't exist. Okay. So, okay, so we did that. We created a coordinate, we printed out its attributes. But you notice when I called it, when I called X, you notice what I do is I just call it with two numbers, 4 and 5. What Python does for you is Python automatically provides the self when that function gets called. Okay. Hopefully that makes sense. And yeah, I mean, if I'm saying anything confusing, please, raise your hands or give me a little notification or something. I should see that in the chat. Let me open up the other chat window and make sure it shows up. And, okay. Participants. Okay, good. Hopefully it should be fairly easy. Now, let's actually define some methods on coordinate, actually make it useful. Okay. So we can go back up to our original definition. And then we want to add another method here that calculates the distance between this object and another object. Def self other. So we can do x squared equals self.x minus other.x. Okay. But passing in the other we're treating the other as another coordinate. We're accessing our own x property and the other guy's x property, and then we square that one. And y. And we return the square root of this guy. Right. Now we'll go ahead and make some coordinates. So how about C1 equals coordinate, and then we do C2. Now I got some coordinates. Let's calculate their distance. We can do C1. Okay, we've just calculated the distance between two objects. So, when we call a method, we use a syntax where we give it the object name, the method name, and arguments to it. Okay. That is, you know what, that's confusing. Methods, they're attached objects, and you call them as methods that are attached objects. You can do some funny stuff with them, but that's confusing. I'm not going to cover this. Okay. So if we just display C1, I give you a main coordinate at some funny number. Well, okay, fine, that it returns something to us, but as users of this, that's not super crazy useful. Okay. So it turns out Python also provides another funny little function called __stir. And you'll notice Python provides a lot of these funny little __ things. They're little special reserved internal things that have a certain meaning. Okay. So if we wanted to make so when you call print on an object, what print does, it grabs that object and it checks, does it have an __ stir method defined there? And if it does, then it calls it. And if it doesn't have a method defined, then it just calls the built-in stir representation. So to make this coordinate look nice, we can do this. Def self. Okay. And here we want to return a little nicer looking string. So we'll do something like return how about stir self.x plus so I'm just concatenating some strings together. Plus quote. So I'll go ahead and remake these coordinates. Ah. Okay, there we go. I did a print on C1, and now it gives me this nice little formatted little text. And honestly, you can have, it totally doesn't matter. I mean, stir, it's just a way to represent something. So you can do my stuff. Okay. And you can put, it's free form. I would recommend formatting it so it's actually a useful object, but okay. So we did that. Okay. So you can make a coordinate. You can print it. So we did type. What is the type of that object? So we did type C1. That is main dot coordinate. Okay, so why? Well, because everything is running in the main module here, in the main namespace. So puts it like that. We can use isInstance to check if an object is an instance of something. So you can do, I believe you can do C1 is and that's true. And then is, okay. Yeah, so yeah, we use isInstance to check if an object is, okay. Um, Classes can have, you can define operators on classes. So this makes it really handy to make objects nice to use. So for example, you saw me using the plus operator on strings. You saw me using the plus operator on numbers. Well, the reason why those are is because somebody already created methods that correspond to those operators. So we have I'll just do add. So we have a little class. We can add, we can make this guy behave look much more like a number. We can do a def, just add. And you'll have to look these up, what all the different operators are. There's quite a few of them. Self. So what we're going to do here is we're going to add the other to this object. So you can do self.x equals other. Do that. And I believe we have to return the self. So you can do remake these guys. The reason why I'm remaking these is because I went to this cell here and I redefined this type, okay? And when I redefine the type, the original instances, they're still pointing, they're still referring to its old type, so I have to remake them with a new type. So you can do C1 plus C2. That gives us print, can do C3 equals. And then we can do print. And yeah, so we C3 is the sum of these guys. So, okay. We can make a fraction like this. We can make a fraction where a fraction implements the division. I believe it's underscore div. Okay. So hierarchies. When we, so in this simple example, I just had coordinate extend object, but you can, I can, if I wanted to, I could have other things, extend coordinate. You can have a lot of really complex hierarchies. I don't recommend doing really complex hierarchies. It makes things confusing. But the idea is when you make an object extend, when you make a class extend another type, that inherits all of the methods and all of the properties on the type that it's extending. Okay. Inheriting something allows you to add more info, that allows you to add more behavior, and allows you to override existing behavior. Okay. So power of object-oriented, I mean, it allows you to bundle, it allows you to package state, it allows you to package really complex behavior inside of an interface. It's an abstraction between the outside world and how those objects behave internally. Okay. So, classes are, they're just one way of representing biological concepts. There are other ways that some people may find more natural. So there's a procedural approach, functional approach. So in Herbert's class last week, we did a lot of processing of, we did a lot of generating data sets, and we did a lot of processing those data sets. So we really didn't really extend any behavior. We used what was called a functional approach to take a data set, perform some transformation and analysis on it, and return some results. So there we really get sort of a pipeline of data flow. And that approach, it makes a lot of sense when we're dealing with processing, analyzing data. So if your background is really more of bioinformatics or the data science type approach, a functional approach really is a really natural fit to a data science way about thinking about things. When we're dealing with physical things, I personally happen to think that an OOA makes a lot more sense because, like I said, exactly how biological cells are, it's just, to me, it seems natural to think about them in terms of objects. But we can't also think about, instead of organizing, instead of a cell or agent-centric approach where we attach all the behaviors to individual types, maybe it would be more natural to group behaviors together. And then when we start dealing with CompuCell does have objects, but your code will be structured in more of an aspect-oriented approach, which is what computer science people like to call this, of instead of grouping things together by cell type, you really group like behaviors together into what's called a steppable. Okay. So there really is no single best way to organize biological concepts. But the one really important thing to remember is there are there are many different perspectives. I mean, sometimes a functional approach makes the best sense. Sometimes a procedural approach makes the best sense. Oftentimes an OO approach makes the best sense. There is no single best perspective of how to go about analyzing things or categorizing things. Okay. So that's basically it for that slide. And that's probably about, go ahead and take a little lunch break here real quick. I will give you a little demo of another package that we are developing, that we're funded to develop. It's called the Mechanica framework. I talked a little bit about this in Herbert's class, but that's another way of looking at things. So if we want to look at how we do self-sorting, and self-sorting is one of the things that CompuCell is famously good at, but this is just another way of looking at things. So what self-sorting is when we have a developing embryo, or usually an embryo or some collection of cells. Cells, they have a tendency of preferring to adhere to other kinds of cells and not adhere to other kinds. They have a tendency of, they prefer to adhere to their own kind because of various surface properties of those cells. So in the yeah, so in the you know what, let me go ahead and answer a few questions here on the chat first. Okay, so on the chat is can you do distance? Yeah, we can do a distance. Yes, can we do a distance of one? Yes, of course we can. We can do, bring this back here. We can do C1 dot distance C2. Okay. C1, oops, we have print C1, print C2. Okay. Add. Let me redefine this. So actually, we want to actually do add as returning another object. We can do return x plus self dot other dot x comma self dot y. Okay, so we can make some coordinates here. We can print C1, print C2. Okay, so there are different ones. So we can do C3 equals C1 plus C2. And yeah, that's the sum of those guys. Yeah, so we had a question, can we do distance between C1 and C2? Yeah, in fact, the distance one, it makes no difference. We can do C1 dot distance C2. and we can do C2 to C1. Can we use the distance function by itself? Yes. But there's a special way of calling it. We can do coordinate dot any method in Python is callable by itself, but you have to call it, you have to specify its full name, which is its full name is the type name dot the method name. So hopefully that answers James's question. Can you have more than one other? I'm not sure I understand that question. You can have as many arguments to a method as you want. Uh, yeah, we can do, we can, yeah, I mean, we could have something like def. Okay, yeah. So yeah, I believe I see. We can do this. So because we've defined the add type, okay, you can do C1 plus C2 plus C3 plus as many as you want. You can do C4 equals, okay, and then we can do print C4. Okay, yeah, so when you define a binary operator, you can, because it's a binary operator between two things, you can actually string as many of these things together as you like. So hopefully this answers your question, right? Is that good? Okay. Okay, great. Okay. So I go back to a little self-sorting example. So in a self-sorting example, we want to create, and I'm bringing this up because this is an example of using a slightly different framework that is a much more of an object-oriented approach rather than and like I said, it's just a slightly different way of thinking about things. As long as it gets you the results, you just need to find a way of approaching things that I think is most comfortable to you and allows you to easily convey with information to people that you're interacting with. Okay. So we can model a self-sorting example like this using the Mechanica framework as where we actually create cell types. So we can create a class A that extends our basic particle type. We can create a class B that extends or inherits from a basic one. We can set some certain properties on there. And then we can define interactions of how these objects interact with each other. And then we can bind those interactions to the types here. So this new framework, it's very, very type oriented. So this entire code here to do the self-sorting is about, let me open up an editor here. This is about 20 lines of Python. So we create a count, we create a count, we create a simulator, we create a couple class definitions, or so these would be cell definitions. we come up with a couple of interaction potentials, and I'm not gonna. If you're interested, I'm more than happy to go over how interaction potentials work. We stick those on the types. We stick a random force onto it, and then we go ahead and run them. And we go ahead and run this guy like so. And this is actually going to be kind of slow because it's running through Zoom. But we can see this is 10,000 cells here. And here I'm using spheres to represent cells. So if we let this guy run a little bit, they'll end up sorting. And yeah, Zoom really slows things down a lot. But yeah, you'll see they'll end up forming little clusters here. So are you looking at the, and Anthony, so are you looking at the interaction potential or the action potential as in a neuron? Because they're actually, yeah, okay. So when we look at the action potential of a neuron, so neurons, they're electrically charged, and then the action potential is basically a threshold of when the charge buildup exceeds and that thing fires. So in this case, I'm using more of a particle or a cell-centered modeling approach here. And here, all of the objects interact with forces, or equivalently, I need to be more consistent in that I sometimes call them forces or potential. But yeah, all the objects interact with forces. So in this example, I created a soft sphere potential here called AA, and this is the adhesion strength between two objects, two cell types of type A, and I set some little parameters there, and I made this one pretty strong. It's epsilon. It's the actual functional implementation is not terribly important, but I set this to be pretty strong in that the A types like to adhere to each other. The B types also like to adhere to each other. And then I made another potential called AB, and then I set its value here as a pretty low number. And find those. Yeah, are these? Yes, exactly. So interaction potentials in a particle-based modeling approach are pretty much exactly equivalent to contact energies in CompuCell. So here, if we let this run, we end up that it starts seeing little domains like this. And if I let this run for another minute or so, they'll end up actually forming blobs. And yeah, that's because, yeah, so contact energy and interaction force, they're not 100% equivalent, very, 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 very similar. Yes, so we have private, so interaction forces. So one, I'm actually giving a talk in SMB on the 17th about mechanosensing. Well, not exactly mechanosensing, more on the lines of receptor binding. But yeah, one of the things that we are developing, we should have it ready here in maybe a couple of weeks, is this new concept that I'm adding called a reactive potential. So what that is when we define two cell types, and then we define an adhesion strength between them. If they get close enough, then that adhesion energy will end up overcoming that activation potential. So just like when we have your normal regular chemical kinetics, if you push two things together, they'll overcome that delta G barrier and they'll end up forming a bond. So what we've done is we've generalized that concept and we've created what's called a reactive potential, where when we push two things together, and if it overcomes some certain threshold, some certain energy threshold or distance threshold, that will actually fire a discrete event, and then you will then have the option of hooking up some code. So when you define your cell types there, you'll be able to add methods here in your class definition, just like we define methods there. And then when that mechanical event gets triggered, it will automatically call that method in your class definition, and then you can attach your custom behaviors there. We're going to have a number of pre-built ones, such as a mitosis or cell death, or various other ones that you can bind those events. But yeah, really, I'm just really in the middle of getting this reactive potential working, and that's actually a really, really great use case. And yeah, maybe we can talk on maybe we can set up a breakout room or something like that. I'm really, really eager to talk maybe on the Slack or something. But yeah, that sort of Mechanica sensing, I think, is a really great use case. And I mean, I'm actually not a biologist myself. I'm actually I'm actually much more of a mechanical engineer / physicist. I do I do a lot of programming just to get things done, but I mean, really, my interest is more on the mechanical engineering side of things. So yeah, so if we let this guy run, it ends up forming these little domains. And if you let it run a little bit more, you'll see they'll actually end up forming little spheroidy clumps. Okay, that's no, binaries right now are Mac and Windows. Unfortunately, I don't have Linux binaries. Uh, yeah, if there's a real demand for Linux binaries, I could try and see what I can do. But it does compile on Linux just fine. But making Linux PyPy packages is super crazy complicated, and I haven't really figured out that whole making Docker images and virtual machines. Yeah, spherical cells. So currently, we have the concept of a particle. And if you choose to represent a cell as a particle, yeah, that works. In a week or so, we're also developing a new thing called a cluster, where you can choose to represent a biological cell as a cluster of spheres. So that will let you do things like actual neuron growth. So one of the use cases I'm using for that is this one. Bring up that one. Oh, where'd it go? So hopefully in maybe a couple, 2 or 3 weeks, we'll be able to do models like this, where you create a soma model, and yeah, where you create a soma, and then that'll actually be able to grow dendrites out as cylindrical as cylindrical elements, and we can trigger a growth. We can trigger a division process when they reach some sort of length or something. And yeah, so these capabilities, if you check back, I'm going to stay really active on the multi-scale modeling Slack. So when we get the sort of dendrite branching, I'm planning on having this maybe in a couple, 2 or 3 weeks. We'll be able to do really complex branching like this. But yeah, and non-spherical cells, yeah, we'll be able to make a biological cell that is a cluster of spherical particles. So you can create little really funny little blobby shapes and actually do more of the complex cell movement, cell shapes that you do in CompuCell. So in CompuCell, your core unit is a pixel. In Mechanica, same thing, but the core unit is a particle. So it's both approaches are really great at doing different sort of things. So CompuCell is really great at doing these contact energies, complex cell migration. Particle approaches are better at doing when you need more sophisticated cell shapes, such as really blobby neurony ones, or if you need a lot of particles. So they're both approaches. They're both really great at doing different sort of things. But you will never ever find modeling methodology that is best for everything. So it's again, it's the same thing of programming approaches, object-oriented, procedurally oriented. They're all totally valid. It's just what's the problem domain that you're working at. And yeah, so I let this run for a few minutes, and it ended up forming this fun little cell clusters. And like I said, the clustering module that I'm currently working on, you'll actually be able to treat each one of these blobs as a biological cell. So that would allow you for really, really complex cell shapes. So, okay. So those are some of the things that we are working on. Like I said, there's an alpha version on PIP. Windows and Mac are supported. If you want Linux and you're using Ubuntu, shoot me a message. I can get you. I can actually get you binaries for that. I can build PIP Ubuntu binaries, but the PIP would not let me upload it because they want this many Linux thing, which is really complicated. You want to do oh, great. Okay, Josh, great. Okay, so go ahead and post a message on the Slack, and I will make Ubuntu 18.04 PyPy packages, and I need to figure out where to upload them because yeah, great. Yeah, I'll go ahead and after we get done here, I will make 18.04 pip packages and upload those to the Slack. Okay, and I'll also post them to GitHub, maybe make it a little more public there. But yeah, okay. So those are some of the things that we're working on. So I'm going to, that's all of the official material I have for today. So I'm going to go ahead and leave the rest of today open. I will stay online and just basically treat this as one giant big hackathon session where I'll be here and a couple other, I believe, Jim and Jim and Javier are probably going to also stay on. So if you have any more tellurians, I'm more than happy to help with those. If you have some biological modeling questions, I mean, uh, Jim Sluka and James Glazier are the real experts on that. I can try and muddle through it, but bear in mind, I'm an engineer. I'm sort of here. I'm not at really advanced biology level, so I'll try and help you out the best I can with those. But okay. Um, for those, I'm happy to demo any new stuff we're working on. So yeah, for you guys who were able to join us for today's session, we really do appreciate you coming by. And we're really hoping that you learn a lot in the upcoming week, and especially for the concepts of taking taking a biological concepts and then developing a model around and then writing down the mechanisms and developing models around those. I mean, James and Jim are really probably the best people in the world to talk to about those modeling conceptualization questions. Okay, well, thanks. A couple other old demos that I can do here. Um, so, so this one here, I'm also running this guy in real time. This is a little mitosis example that I threw together in